Thank you, Ron, and thank you, Paul, and the organisers and the Physiological Society for... I say thank you, but you know what it's like. About a year before you accept the invitation to give a talk, and then about a week before, you look at that invitation and you find, my goodness, I've got to talk about the physiological, psychological responses to cold and human adaptation to cold, which is actually everything I know. So we're going to do a bit of an overview, and it's not an easy area because it's fairly confused, particularly when we come to human adaptation to cold. And part of the reason is, unlike altitude and heat, man in the cold is not necessarily a cold man. And there's some confusion. You can put people into very cold environments, but if they are protecting themselves or exercising, then the tissue profile may not be one of cooling. I've just got one slide that will help you remember that, and that's a lovely slide from back in the 50s, which was a Burton and Edholm slide showing you the size of the glove you need in order to protect peripheral temperatures. Here we are, this is it when you're at rest at minus 32 degrees Celsius, and of course as you exercise, then once you get to strenuous exercise, no mitten is required. So we need to concentrate not so much on ambient temperatures when we talk about cold as tissue temperatures. And that's what I'm going to do. I'm going to look at the skin, the superficial nerves and muscles, and the deep body temperature. Okay, what sports is this relevant for? Outdoor pursuits, sailing, fishing, triathlon, open water swimming, and normal sports that people now sometimes choose to do in extreme environments, with increasing numbers doing that. And it's just worth remembering that cold is the biggest killer of sports people undertaking their sport. And what's the pathologies? Well, there they are, cold air, and they range, and cold water, they range from just breathing cold air through freezing, non-freezing cold injury to hypothermia, drowning, sudden cardiac death. Clearly, I'm not going to have time to cover all of those, so I'm going to concentrate, as I say, on those that are evoked by skin, superficial, and deep body cooling. Okay, let's start with skin cooling. So we know that a rapid fall in skin temperature evokes a cold shock response. That's uncontrollable cardiorespiratory responses, very difficult to breath hold, very easy to aspirate the 1.5 litres of water you need to cross the lethal dose for drowning. Peripheral cold receptors, 0.18 millimetres below the surface of the skin, initiate this response. And you know that you're doing a fairly risky experiment when you replace your independent medical officer with a priest. Next slide, please. Thank you. Now, obviously, an uncontrollable respiratory response to immersion makes swimming pretty difficult because you have to swim within the swim cycle. So this is just evidenced here where you see people who could happily swim for 10 or 20 minutes in water at 25 degrees Celsius, and you can see 7 out of 10 of them failing when you plot their respiratory frequency as a percentage of that they showed in warm water. And clearly those that are hyperventilating are finding it very difficult to coordinate breathing and swimming. The successful swims in very cold water, this is 5 degrees now, are those that don't have a big respiratory response, and this guy is a Navy diver. Don't use them as a subject. Next slide, please. 80% of those that die in triathlons die during the swim phase. And next slide, please. And we think that one of the precursors to that is co-activation of the cold shock response and the diving response. So the cold shock response, as I say, initiated by skin cooling, the diving response by stimulation of the ophthalmic division of the trigeminal nerve around the face. And as a consequence of that, you see a confused ECG. So if you ask people to coincidentally have a cold shock response and they get some face immersion and they hold their breath, within about 10 seconds of breaking their breath hold, you'll see a fairly confused ECG. This is human data. And you can actually reproduce that in an isolated heart model. So this is some work we've been doing with Mike Shattuck's group at King's College with the infusion of adrenaline, noradrenaline, and acetylcholine to recreate that conflict between the cold shock response and the diving response, or autonomic conflict, as we've called it. We can produce this in about 80% of people if we just put them under the water and ask them to breath hold for a reasonable period of time, within 10 seconds of breaking that breath hold. Whether or not that descends into a fatal cardiac arrhythmia will depend on lots of predisposing factors and the presence of them. One of the questions we've had in the sports field is why are so many people dying during competition that don't die during training? And we think it's because there's a combination in competition of anger, obviously being in a competitive environment, water entering the nasopharynx as you try to breathe and you can't because there's a plume of water over your face, extended breath hold. And they wouldn't normally be present during open water swimming. And of course, because this is an electrical disturbance of the heart, you don't see it at post-mortem. And anger, just out of interest, is the one emotion which coincidentally activates the sympathetic and the parasympathetic nervous system. So why do you become angry? Well, because that's what a mass start to a triathlon looks like. Okay, let's go on. Next slide, please. Okay, let's talk a little bit about now, we've called the skin, now we're going to call the superficial nerves and muscles. And there's just a short clip of video here showing a guy who's perfectly happy swimming in warm water, a pretty accomplished swimmer, and now he's trying to do the same in water at 5 degrees Celsius. And I'm only showing it because I want you to look at the expression on his face at the end of this 7-minute swim. And he looks pretty exhausted. He's gasping for breath, so we have to try and understand what that is. That's classic profile of somebody descending into swim failure. And of course, if you want to look at the effects of cold, you need to have a big driving function. So trying to swim in 5 degrees is a pretty big driving function to see what's going to happen. Of course, water at 5 is about twice as viscous as water at 25, so there's a problem associated with that. But classically you see, and you see the same in people who are running and getting cold, you see a decrease in swim length, stroke length or stride length, and you can see an increase in frequency. And people move from this position into a more upright position, sinking force increases, and they're moving towards swim failure. And you can see that by looking at the distance they travel for every litre of oxygen consumed. And here you can see in black what happens in water at 10 degrees C, going down to about 1/3 of what they can achieve in warm water. And it's been reported that running and cycling at the same speed and intensity elicits a higher VO2 in the cold, particularly at low levels or low intensities of exercise, because as exercise gets greater in terms of its intensity, the shivering, which is coexisting with that exercise, is suppressed by skeletal muscle activity being used for the exercise. So the performance impairment you see with cooling, with this superficial cooling and skin cooling, is caused by shivering, which is increasing the requirement for carbohydrate oxidation, and improves and results in quicker glycogen depletion. Also, the co-activation of agonist and antagonistic muscles impairs performance. There's increased motor unit recruitment in order to maintain the same force production as the more superficial muscle fibers become incapacitated by cold. Decrease in muscle tendon elasticity, increased stride frequency and decreased stride length, I've mentioned, and a lower mechanical efficiency due to these called neuromuscular functions. And this decrement can be produced by cooling the skin below about 25. It doesn't actually require a great fall in deep body temperature. And just a sort of summary of what's going on, therefore, from various authors. You can see as workload increases, this superimposition of shivering that's occurring down here is gradually reduced, but you still have a higher VO2 for any given level of submaximal work because of the list I just gave you, and then a lower VO2 max. And because of the various factors which we've discussed, you get an earlier switch to anaerobic metabolism, which is one of the reasons why that guy, after 7 minutes of exercise, was looking so exhausted. He's working anaerobically as he gets a whole range of changes associated with decreased muscle temperature. And some of them are listed on this slide. I won't go through them all because time won't allow. But in particular, you're seeing reduced enzyme activity, rate of conduction and repolarization of action potentials is slowed, and a decrease in muscle perfusion. If we look at the last one of those, the muscle perfusion, as water temperature falls, you see a reduction in muscle blood flow, and it occurs even when you're exercising quite hard. So that's the cold-induced muscle vasoconstriction overriding the exercise hyperemia associated with the performance of that exercise. In terms of sort of neuromuscular function, below a local temperature of 20 degrees C, the conduction of action potentials is slowed and the amplitude reduced, as we mentioned. Nerve block at around about 5 to 15 degrees Celsius. Maximum power output falling by about 3 degrees C per degree C fall in muscle temperature. And it's particularly the rate of force application and its removal that's affected by cooling. So dynamic exercise performance, especially fast velocity movements, is generally more disturbed by cooling than isometric contractions, and you see a shift to the left in the force-velocity relationship with lowered muscle temperature. Just a quick word about hypothermia. So now we've cooled the skin, we've cooled the superficial nerves and muscles, and we're now cooling the deep body tissues. And the next slide, please. There we are. There's the signs and symptoms of hypothermia. I'm not going to go into these in great detail, but just note that the first major organ to be affected is the brain, with a reduction in temperature of just 3 or 4 degrees Celsius. And that explains why cognitive function is impaired in the cold, due to a direct effect of hypothermia on neural function, and also because actually the pain and the discomfort associated with being in the cold is distracting from some tasks, and tasks that require a high level of concentration and focus are easily impaired by the cold. Also explains by repeated exposure, adaptation to cold, that significantly improves thermal comfort and decreases the pain experienced in the cold, can also improve performance on those tasks that require high levels of concentration. So there's all of the changes you see with hypothermia. Just to summarize them, we say hypothermia affects the cellular metabolism, blood flow, and neural activation of tissue. So you see lots of decreases, impaired, and cease on that slide. Now that can, in some circumstances, be beneficial if you happen to be in a situation where you need to have some protection against hypoxia. However, if you're trying to exercise, none of them are of any particular benefit. And there's an enormous variation, which is why there was no time on that signs and symptoms graph. There's an enormous variation in the speed with which people cool. So here you have the half-man, half-weddell seal up here, who in 18-degree water can maintain deep body temperature. 18 degrees will possibly be the temperature for the open water swimming events in Rio. Thought to be 22, but it's looking like it might be a bit cooler. And here we see an elite athlete who's cooling at around about 4 or 5 degrees Celsius per hour. So this guy had better be fast. There are no slow, thin open water swimmers. And the variation that you've just seen there is caused by a whole list of thermal and non-thermal factors. And the one which I've highlighted there is the one which I'll move on to talk to you about now, which is adaptation. This is something of a minefield, really, in terms of, we thought that altitude and heat were confused, but cold adaptation is at a different level for a whole host of reasons, not least of which is that we avoid the cold like the plague. So we've been able to do that for many years. So the oldest man-made building is a windbreak constructed by Australopithecus about 2.5 million years ago. And of course that means that we don't see the morphological and anthropometric adaptations that you see with other animals. And it also means that when people have studied human adaptation to cold, they've had to go and look at a wide variety of groups that happen to be exposed to cold, from ethnic groups through to sportsmen, expeditions, seasonal changes, and then some laboratory work. And if you look at the heat balance equation, in theory, the body can respond in one of 3 ways to a cooling stimulus. It can increase its metabolic response, we call that metabolic adaptation. It can increase its insulation, either passive, more body fat, or through vasomotion changes. That's insulative adaptation. Or it can just let its deep body temperature fall, become like poikilothermic-like. That's a hypothermic adaptation. And habituation, as you know, is a decreased response to a constant stimulus. And so it's worth just keeping those in mind, because which adaptation do you develop? Well, people have suggested that it depends on the degree to which the exposures result in significant body heat loss, so repeated short exposures with trivial change in heat loss in the body can produce habituation. Repeated or prolonged severe cold exposure resulting in a fall in core temperature, an insulative adaptation, or one where the thermogenic response can balance the heat loss from the body, may result in a metabolic adaptation. That's Young's suggestion. Others have suggested that it depends on diet and fitness. People of high fitness and low body fat produce a metabolic adaptation, low fitness, an insulative adaptation. Others suggest that it progresses from metabolic to hypothermic to insulative with time exposed. So there is no agreement generally about the human adaptation to cold. One thing we do know is that the cold shock response will habituate. So 2 out of 3 members of this family think that repeated immersions in cold water are good for you. This guy's not so sure. But mum and dad, as always, are correct, and you can about reduce the cold shock response by about 40% with as few as 5 or 6 3-minute immersions in cold water. And that reduction lasts about 14 months, was the longest we managed to keep testing people before they refused to come back anymore. If you repeatedly immerse one half of the body, you'll get an adaptation or habituation of the cold shock response. If you then take the wetsuit that you've been protecting the other half of the body with off and turn the person around the other way, you'll see exactly the same habituation of that response. So that response is habituating somewhere more central than the peripheral cold receptors. And we've seen that with prolonged exposure, chronic exposures in animals, and also with this study, which we did with humans. Glaser and Griffin have suggested that the frontal cortex is important for the development, but not the maintenance of habituation. But beyond that, we know little about the mechanisms that produce that habituation. I have psychology in the title, so here's some psychology, and there are a range of psychological skills training that people give to athletes to help them perform in the extreme environment of a packed stadium. And we did have some interest in whether or not those same psychological skills, which you can see up listed on this slide, would also work in an extreme environment. And so we we looked at a group where we gave 2 cold water immersions, which is a control group you can see here, and between those two control immersions, nothing happened. This group had psychological skills training along the lines of the 4 we just listed, and we found an increase in the ability to breath hold on cold water immersion by about 80%. In another group, we had breath hold 1 and breath hold 2 separated, so that's 2 immersions, a week apart, separated by cold habituation. And this group had cold habituation plus psychological skills training. And we saw a bigger improvement in breath hold time. So psychological skills training can improve your ability to hold your breath on immersion in cold water independent of the physiological adaptation. The suspicion is that the physiological adaptation is decreasing the drive to breathe, and the psychological adaptation is improving your conscious suppression of that drive, which is why psychological skills training tends to work with responses that are under voluntary control. So we can get people to run further in the heat by giving them psychological skills training. Can you adapt to the neuromuscular decrements which we saw earlier in terms of things like grip strength, manual dexterity? Well, unfortunately, the answer appears to be no. From the evidence that you see, even from the animal literature, so animals active at low temperatures have a lower performance capability at those temperatures than their muscle systems could achieve at higher temperatures. In terms of human work, there's been no evidence that cold adaptation improves things like manual dexterity in the cold, even though you can produce a cold-induced vasodilatation that can keep the hands slightly warmer as a result of repeated exposures to cold. There's been animal work which suggests that with repeated exposures to cold, you get a shift in muscle fiber type, and chronic exposure to cold increases capillary density and capillary to fiber ratio, primarily in oxidative muscles. And for a while, that kind of result was being translated into the diving women of Korea, the armor. However, having in 2003 got the idea that decrease in fibre size and increase in capillarity occurred in these divers, that wasn't supported with 14 Indonesian breath hold divers in a subsequent study. It's an interesting point that requires further investigation. So those ethnic studies, which there's Stanton, Hicks and Willie O'Connor. Willie O'Connor was a reader up at Leeds University, looking at the metabolic and thermal responses of Aborigines in the Central Australian desert in 1935. There's the diving women of Korea, the Ama, and the Ainu, the diving women of Japan, and they dive in the winter for seafood, etc., in water as low as 10 to 12 degrees Celsius. And they keep diving until their core temperature gets to about 35 degrees Celsius. They don't know it's at 35, but that's when they seem to stop. But the problem is, if you look across, and it's an enormous and confused literature, you can see every type of potential adaptation I've talked about demonstrated by some ethnic group, Aboriginal people. And that may well be to do with the nature of the methodology, it may well be to do with the nature of the exposure, but it doesn't help us particularly get a clear picture of human adaptation to cold. Genotypically, it's fairly interesting that over the generations, the surface volume to ratio of those from cold areas is less than those from warm areas, which you would expect because that's oxygen conserving. And also, if you look at indigenous populations to cold environments, Siberian in this case, then the candidate cold adaptation genes that show the strongest signals of positive selection are those to do with energy, regulation, metabolism, and vascular smooth muscle contraction, as you might expect. The human response from the laboratory is to show a adaptation or a habituation of the metabolic response to cold, and it tends to be in people who are sitting still in cold associated with a faster fall in deep body temperature. It's a hypothermic adaptation underpinned by an habituation of the metabolic response, and this is a study we did some while ago, resting individuals, but you can basically see that pre-adaptation, this was the relationship between fall in the rectal temperature and oxygen consumption, which is the analogue of shivering in this situation. And you see that there's a reduction with repeated exposures. This was 9 45-minute exposures. There's a reduction in the shivering response, but it stays at the same sensitivity. So it's just an offset. There's an offset in the threshold for that shivering. Stanton, Hicks and Willie O'Connor had asked in the 1930s whether or not the reduction they saw in the shivering response of Aborigines and the faster fall in deep body temperature would continue to the point of hypothermic death. And it only took us about 80 years to answer that question. But it was quite an important one, of course, because it relates to the elderly, people living on the streets, people, divers. And so the study we did, we looked at a fall, the metabolic response to a 2-degree fall in core temperature. Then we repeatedly exposed people to a 1-degree fall in core temperature. Then we re-exposed them to a 2-degree fall in core temperature. And what you can quite nicely see is that those that had the fall in core temperature of 1 degree here, as soon as they went beyond the point that they were used to in terms of a 1-degree fall in deep body temperature, they responded with a normal metabolic response. So they didn't stay suppressed all the way to a hypothermic problem. They just come back to normal. So in terms of deep body temperature responses, in terms of the shivering response, it's specific to the profile that you experience on repeated exposure to cold. One of these other groups had repeated skin cooling without any change in deep body temperature, and we saw no metabolic adaptation there. So there is just a shift like this that occurs with repeated exposures to cold. The adaptation appears to be specific to the deep body temperatures, gain remains unchanged, and the site of adaptation is central to peripheral cold receptors. We didn't see it with repeated skin cooling. And there's been work done earlier that's suggesting that downregulation of thermoresponsive cells in the reticular formation is the mechanism underpinning this shift. And the other thing, of course, that is beneficial in reducing the shivering response is the co-activation of agonists and antagonists, and the interference that you get with performance of exercise is reduced having habituated that metabolic response to cold. So that just shows you quickly how that fits in with, there's your normal shivering response, that's what happens with cold acclimation, and there's age and hypoglycemia, just to put the the thing in context. One of the things that has certainly seems to happen when you're now exercising cold water regularly is there is increasing evidence, some of which is fairly recent with us with children and serpentine swimmers and groups like that, outdoor swimmers, that actually with repeated exposure to exercising cold water immersion, that you develop an insulative adaptation. So people cool more slowly if they're used to being in cold water. Even if they're swimming at the same intensity, they're in the same water temperature, they've got the same level of body fat. So this suggests that this is underpinned by a change in peripheral blood flow. It's a vasomotor adaptation that produces an insulative response. So they cool more quickly if you sit them still in cold water, but they cool more slowly than controls if they're exercising. I'm going to say one word about non-shivering thermogenesis because you can't do a talk on human adaptation to cold without talking about brown adipose tissue. And for many years it was thought not to have a role in adult humans. Now it's thought that it does. It becomes active in the cold, and non-shivering thermogenesis with repeated exposures to cold increases from about 11 to 18% in terms of its contribution. But overall, in terms of defending against a very cold environment, the role of non-shivering thermogenesis is small, less than 30% of resting metabolic rate compared to up to 500% from shivering. So there's no evidence that brown adipose tissue thermogenesis can increase to levels that will defend core temperature in acute exposures. I'm going to finish because one of the things that is my hobby horse at the moment is we've had 4 speakers here today, one on altitude, one on sleep, one on heat, and one on cold, because that's just the way we like to arrange our disciplines. I'm cold, wet, and nasty, and George is hot and sweaty. You know, that's just the way it's done. But of course, that's not what it's like in the real world. In the real world, the Aborigines were experiencing very high daytime temperatures, very low nighttime temperatures. People who go to altitude are also exposed to very cold environments. And between the 64 years leading up to 2012, we did an analysis. There were only 23 papers that looked at combined environmental stresses in terms of their impact on the body. I'm pleased to say that that number is going up now fairly quickly, but it's clearly an area that requires further consideration. And we thought, well, we'd go one step further at this stage, and some earlier work by Hessemer. When you acclimatise people to heat, you also see a shift, a downward shift in their shivering threshold. So that's a cross-adaptation. And we wondered how that might work between those combined stresses of cold and altitude, which you obviously get when you go to altitude. And it's based on the fact that an adaptation to an environment has an effector specific response, might be a sweat gland, a red blood cell, but it also has a generic response component, which is possibly autonomic nervous system. So can you get cross-adaptation? And the answer is you can. If you expose people to exercise at altitude, and you then give them a cold shock habituating program, so just 5 days of repeated cold water immersions, just a few minutes, one in the morning, one in the afternoon, and then you put them back to altitude, and you compare their responses on that second exposure to altitude with a control group that have just done repeated thermoneutral immersions, you'll find that those who have had cold water adaptation, cold shock habituation, will have decreased adrenaline and noradrenaline concentrations at altitude. They'll have a high frequency component of their heart rate variability is higher, and the number and severity of the symptoms of hypoxia are reduced. So the conclusion from that is that a generic autonomic cross-adaptive effect exists between cold habituation and exposure to acute hypoxia in humans. Again, it's a very, very new area, but it's interesting because it might prepare people for the real world rather than from the subject areas that we tend to research. Summary. In terms of performance, so we've got the response, the performance impairment, and the possible benefit of cold adaptation. Cold shock autonomic conflict can produce swim failure, panic, discomfort, cardiorespiratory hazards, including sudden cardiac death. And the habituation of the cold shock response should be beneficial, certainly in terms of performance of exercise in cool or cold water in the first minutes of that performance. The peripheral neuromuscular cooling, the performance impairment you see with that, there's limited possibility for improving that with repeated exposure to cold. Skin and deep body cooling, causing the superimposition of shivering, co-activation of agonistic and antagonistic muscles, hypothermia and muscle function. While the habituation of shivering should be beneficial, the development of an insulative adaptation, if we knew exactly how to do it, would be beneficial. And there's still big question marks as to whether that which has been seen in the animal literature with regard to capillary density, capillary fibre ratios, shift in fibre type proportions, is actually seen in man, but that could have some potential implications as well. Thank you for your time.